We should wait 1 or 2 minutes. So let's wait. Come in. Still plenty of room left. So let's wait 1 to 2 minutes to get started with everything. Thank you very much. Okay, all right. So first of all, wow, thank you everybody for coming. I'm happy that so many of you showed up. It's very exciting. Mainly because this is a little bit of a different talk right now. So you had lots of talks where I hope you got some applicable insights for you and your work. You are now here together with me in my own personal therapy session, because what I'm going to show you is a project that I've been working on in the last 4 years. I'm finally able to talk about it. And I need to share so much stuff. And don't worry, in the end, it's not just me complaining and moaning and swearing, most likely. I will also have some insights, some learnings that I want to share with you. Come in. Before we start, I want to show you this particular image here. It's a cover of a book that I bought around Christmas. It's a very old book. It's from the 1990s. And look at this particular image and try to figure out what it means or what it refers to. I've even written a little haiku. Yes, I can do that. I had a tool for it to validate that it's actually a haiku that explains what's going on in that image, and the explanation is very important. It's a hero with a cape on top of a dragon rescues a princess. On his long journey, he battles fierce animals and rides a dolphin. So this is what's happening in this image, or this is what the image should depict. And look at it, memorize it. We are going back to it later, okay? That's just a little side note. We are looking at it later. What I actually want to show is an architecture journey. So I'm working at a company called Dynatrace. Who of you knows what Dynatrace is and does? Okay, wonderful. Okay, this makes a lot of stuff easier. And I've been in the project to revamp and re-architecture our user interface and the way we at Dynatrace ourselves are writing applications on the Dynatrace platform. And I was particularly tasked with one part, which is a serverless backend. I'm going to detail you on what we want to do with the serverless backend in just a couple of minutes. And over the last couple of years, this project evolved into something very cool and very exciting and also very challenging. We are here at the Global Azure conference, and especially on Azure, we had lots of challenges that we needed to overcome, and I want to share them with you. So what is our serverless challenge? What is it what I'm talking about? Come in, don't worry. What is it when I'm talking about we want to create the serverless backend and we want to rework the way we at Dynatrace write applications? So this is one screen from the new Dynatrace user interface. And if you look at it, actually just this little piece here on the left side, that's the new Dynatrace UI. So that's everything that we at Dynatrace provide for all the other people to write everything on the right-hand side. So we have lots of different small self-contained applications contributing to a bigger platform. And all we provide is some hooks so you can load your application into our environment. You can call the right APIs. We do the routing for you. But what you do in those applications is totally up to you. And that's the idea of the new Dynatrace. That's actually a thing that a challenge that we faced on our own. We suddenly had about 1,000 developers and everybody should be contributing to the same code base. This doesn't work. So what we did is splitting up the code base in self-contained applications and provide some infrastructure so people can work in an integrated environment. This is called the Dynatrace App Engine. And we don't constrain ourselves to Dynatrace developers. No, we give the same tools to our partners, to our customers, and everybody else who wants to have access to the Dynatrace platform. They should be able to write applications, contribute to the bigger picture, and do basically whatever they want, which is, a challenge in itself. we have one big data store for all the monitoring data that we have, great. And App Engine is there to write those small self-contained pieces of code that make up the bigger picture. And not only on the user interface, but also for automation and workflows. So it's possible that if some certain event happens, it triggers a workflow, and this workflow also executes one of those applications that have been contributed to Dynatrace. So if you ever get a Slack message because some server outage has happened, this Slack app has been written by somebody not in the core team. They are within Dynatrace, yes, but it could be just anybody, partner, a customer, whatever. If you as a customer have your own communication tool available, then you can write the integration for it yourself. So that's the overall idea. And for that, we also need to execute backend code. And we decided early on that we want to have backend code written as serverless functions. So you write a little bit of JavaScript code deployed on our infrastructure and run it whenever it's necessary, either as an HTTP call from a user interface or when an automation workflow triggers in the background, asynchronously. And serverless has two sides to it, which are very interesting, especially for what we did. First, serverless from a developer's perspective means that you don't write any servers, you just write the little piece of functionality that you're actually concerned about. Good. And serverless from an infrastructure perspective means that you don't manage any servers. The servers or the containers or wherever it runs it are provided for you. And there are two sides to that coin. All right, this is what we wanted to solve. If there are any questions on that, I'm happily, you can ask them, answer them, but for a moment, let's sink it in. Let's imagine that you, even if you're not a Dynatrace developer, can contribute to Dynatrace and work with the same tools that we do in the company. All right, next chapter. Lambda for you. Who knows about AWS Lambda? Okay, right. When we started out, we wanted to make sure that we don't fall into the not invented here fallacy. This is something that we Dynatracers love to do. We see things and want to do it better, and most of the time we also succeed with it, but here in that project, we particularly said, no, we want to use what's already there. We want to make sure we were a small team, 5 to 6 people. We wanted to make sure that we use what's there, run with the community, run with what's out there, and not try to make everything on our own. Hello. And this was one of the rules that we as developers set for ourselves. One of the rules that we got from project management was, well, it needs to run multi-cloud. So not only on AWS, but basically on every cloud that's out there. Azure, GCP, you name it. And this is not so easy. Actually, I have a much better visualization for that. It's actually multi-cloud. It's very scary. It's not something that you do every day. So with the premonition of running multi-cloud, we tried out basically every serverless platform that runs on Kubernetes on our own servers or on AWS or Azure. We tried OpenWhisk, OpenFast, Fission, Knative, Kada, Kubeless, and basically everything that was a Western serverless platform like Crustlet, and I've already forgot how they have been. And I'm not very nice with all those scary smileys there. They are good solutions. They are just not the solutions that we have been looking for, unfortunately. Especially, the Western stuff. It's fun, it's exciting. We heard lots of stuff on it, and all of those POCs are now basically dead. So none of them exist anymore. Thank God we didn't work with those and try to fix them or integrate them in our environment. And those who aren't dead are set out to die in some VC-funded startup. So this is the sad state of it. I could talk at length on what was wrong. No, not wrong. Why those solutions didn't fit our case. But I won't do that because I want rather talk about our case. And that's okay. So all the solutions have been developed for a specific use case, and that was not ours. Even though there are serverless platforms where you deploy some application and can run it in a serverless manner, we suddenly weren't people who were writing applications and deploying them. We were an intermediate infrastructure provider. We at Dynatrace had a different role now. We are not developing applications. We are providing a platform so others can develop applications. And this particular view was the reason why we couldn't use any of those platforms. Those use cases were not ours. And we could either try to squeeze our use case into that particular box and fail, or we tried something different. And what we did early on, so after trying all of them out and failing with some of the requirements that we had, we said, you know, the one thing that actually works best for us right now is AWS Lambda. Lambda has a couple of features that are unique to that particular serverless platform as opposed to all the others. Let's run with Lambda, even though we know we need to be multi-cloud at one point in time, and learn what it means to have a serverless platform going. Focus on function development, focus on the developer experience, focus on tooling. Try to get one of the steps out there before trying to fix everything where you don't even know when it's going to happen. It's the first big learning. Start small. And we came up with this particular architecture. It's actually very simple. So this is the Dynatrace part. We have the application gateway where all those requests are coming in. If this is a request to a function execution, it hits the function proxy. The function proxy then invokes a Lambda that's deployed on AWS. So we package our apps in one specific Lambda. This Lambda is being booted up, being executed, and we get the result. AWS Lambda gives us a couple of things that are actually quite nice. So first of all, you can scale and limit CPU and memory pretty nicely. So you can say, you know, you just run with a fraction of a CPU, you just have 265 at 56 megabytes of RAM, and that's it. Or you go for 512 and have a different CPU attached to it. We know how to limit resources, especially if you want to run workloads from other people. This is very, very helpful because you don't want them to, I don't know, use 6 CPUs just because they request it and all the other executions that run next to it are dying, basically. One thing that is interesting about AWS Lambda, which was odd at first but very beneficial to us, is that you get one Lambda instance per invocation. If you have a second invocation, a second function call, you get a second Lambda instance. Since they are so small and disappear after execution again, AWS Lambda can guarantee that. They can do that. Which means that instead of having a couple of servers, I don't know how many, which handle a lot of requests, you have tiny, tiny, tiny instances that handle just one request, one at a time. Which also means if you want to scale, well, at AWS Lambda, we can scale up to 1,000 parallel invocations, which means 1,000 parallel instances. Actually, we have a contract with AWS, so we can go up to 3,000, but that's a detail. Also, if one of those, and this is the most important part, by having one request isolated per Lambda is actually important, is that if an error is happening and the runtime that runs this code is crashing, it just affects this one particular instance, no others. So this is great. So if one of the people who contribute to our platform, again, untrusted code, can come from anybody, crashes the operating system for whatever reason, it doesn't matter. We just respawn it. And all the other requests and run in parallel still work. And this is why Lambda fits so well to what we wanted to do, because we want to run untrusted code. Which also means if you have noisy neighbors, you know, they eat up RAM, they eat up CPU, or they crash all the time. It doesn't matter. All the other invocations still run. So this was set. Now we could focus on how are people going to develop this. The universal function interface. I'm actually very proud about that. So this is your typical AWS Lambda code. It has changed ever since, but back in the day when we started out, it looked like that. You have a handler function. It's some function that gets an event in a context, and then since apparently it's being called by HTTP, you prepare an HTTP response. And everything that I highlighted yellow in there actually is a lot of domain knowledge of AWS Lambda and how it's invoked on top of that code. And this is not easy. So you need to know that you're returning an HTTP code, even though maybe you're not called by HTTP, you need to know upfront if that's an HTTP function. And everything that's an event and context is also very, very much connected to what AWS Lambda offers to you. And for us, this was way too much to handle. So we thought, okay, this is complicated. You're learning a domain that might not be yours. And again, we wanted to be multi-cloud. We wanted to be, so actually nobody who develops for us should know that it runs on AWS Lambda. This is why we decided on one particular JavaScript interface. We export a default function that gets a payload. The payload is your input parameters, whatever that is. If it comes via post, via get, or if it doesn't come from HTTP at all, it doesn't matter. We don't care. You just need to work with that. You're getting the payload and you return a response. And the response that you return also has no connotation of HTTP in any way. It's just getting shit in and putting shit out, and how it's called and what's all the steps in between don't matter to you as a developer. And it's as simple as that. And the thing is, we decided on the function interface pretty early on, about a half year in, and we haven't changed it since. Everything else has changed, but this hasn't changed, which means our developers who produced code 3 years ago can still run it, even though everything else is different now. And this was the second decision that we made. Make it easy, make it simple, remove everything that could clutter your interfaces, remove everything that could confuse developers. And yeah.
Can I go back to the previous slide?
Sure. And that's an animation, which means that I need to run the animation again. That's if you want to have drama in your code and your slides.
So the payload is just a dictionary, right?
It's a JavaScript object, yeah. So JavaScript objects, you can think of it as a dictionary, yes.
So aren't there semantics in the set of allowable names in the dictionary, and don't those in fact constitute a contract?
No. That's totally up to you.
I want to learn how you did that.
That's totally up to you as a developer. We don't care. You can define the interface. We just and when you call the function on your own, so you know the contract up front. And also, if you integrate it with automation, you also provide the configuration part. So you then again have the same names again.
I see. So it's up to the user to define the contract.
Exactly. Okay. That's the thing of having an open platform. It's totally up to you, to the developers. And this is why keeping it easy was also so important. If we would have added our domain on top of it, those contracts change, especially over time. But now it's just your contract, and all we say is that keep the invocation part to us. You focus on the development, and the invocation details have been moved outside of AWS Lambda, outside of our serverless platform, into the API gateway, into the function proxy. The function proxy knows how to do an invocation. The function proxy needs to do a lot. They need to get all the meta information. They know what to provide to the runtime, but you as a developer don't care about it. The funny thing is, so this was a decision that we made early on in our project, and apparently we had a hunch, because once we had it and we published it, other platforms like Netlify or Shell, who are also providing serverless backends, followed suit. They are now having also very simple, similar function interfaces, getting rid of lots of extra stuff around it, or just having it as a small add-on afterwards. Also, AWS Lambda has now a different interface, which is much easier to read. We are in contact with AWS since the beginning, so that's nice to see. Serverless interfaces have become much easier ever since, and apparently we were on the right track. Something that we also did, which is very interesting, is that since we wanted to keep it easy, and we are a totally different part of our infrastructure, calling back to Dynatrace is actually quite complicated. So we said that if somebody does a fetch call to one of the Dynatrace APIs, and we know it because it starts with the /, then we intercept this call and append all the extra stuff so you can safely call back to Dynatrace. Authentication tokens, domain names, whatever meta information they need. And we can do this in Node.js. We can do that in different JavaScript runtimes as well, by providing a separate VM context. So you run Node, then inside you run a VM context. And in there you say, okay, I'm providing a fetch function, but this fetch function is mine. I'm going to rewrite a couple of things and push that stuff out. Again, focusing on the developer, this makes it easy for them to call back to Dynatrace. They are totally oblivious that they live in a different part of the infrastructure. All they do is calling an API like it would be next to them, even though it's basically it could be theoretically on the other side of the planet. Theoretically. Okay, that was good. That was nice. People were developing applications. Then we got the next challenge: ad hoc functions. This is a concept that's unique to us, I guess. This is the Dynatrace workflow screen. We have a workflow here where you can connect different tasks. And there's one task that says run JavaScript. This file is from me. That's not in our UI. But what this task allows you is to execute any JavaScript written in the browser on the backend. Any JavaScript from anybody. And since it allows JavaScript from anybody, everybody is writing it. And I'm getting goosebumps just thinking about it. So, and if you think about that, we are reusing those instances again. They are not being shut down, but reused over and over again. JavaScript is a very brittle language. And even though we have this VM context around it, it's not secure. This is also what the VM documentation from Node says. It says here the VM model is not a security mechanism. Don't use it to run untrusted code. We run untrusted code. And those are two bugs that you can inject. So first one, with this constructor, and some string, you are basically escaping the sandbox and are back in your node process again, and where you can do everything. And you could do things like that, overwriting console log, and say, well, if you are calling console log, which basically every JavaScript developer does, let's do a couple of nasty things, like sending your log line to another backend or wherever. And since we are allowing Node.js dependencies, you would have been able to install a library unknowingly that basically leaks all the details to some nasty player. That was pretty scary, especially if you think about it, that you can inject something like that by just opening a browser, writing it, running it once. It ends up in one of those 1,000 AWS Lambda instances. You don't know where you run any application, and you're basically infected. So we made a decision there. First, okay, we were losing the app concept. Now you should be able to run any JavaScript, okay? We allow the execution of arbitrary JavaScript with no guardrails, no upfront checks, and written in the browser. And to solve that, we moved to a different platform. We moved away from Node, we moved to Deno for a particular reason. Deno provides Rust bindings to V8, and we know how to write Rust. So we had Deno, we had a couple of Rust developers, and we say, okay, we can combine this. We can use those Rust bindings, write our own global scope, make sure that if you have any HTTP call outside, it doesn't go to anywhere we don't want to. And also one thing, I don't know if it's here on the slide, we were also able to say that after this invocation, we throw away everything, and with the next invocation, we start anew. So you don't have any remnants in your code, you don't have any memory remnants whatsoever, everything will be deleted. And with that, also deployed it to Lambda, we were running ad hoc code, ad hoc JavaScript code on AWS Lambda with a new invocation with every execution. So basically, our first ad hoc runtime was taking Deno, removing the Deno libs, adding our own custom globals, adding the Lambda bootstrapping, and that's the Dynatrace JavaScript runtime, or the first version. And this was a huge security boost for us. And actually, if you think about it, when we were talking about the other JavaScript functions that we already had written in Node, we found out that we don't need as much Node as we thought. We couldn't run as much Node as we thought because most of the interesting stuff is compiled natively, and AWS Lambda can't run something that you compile locally for Windows or Mac on the Linux machines, so people weren't using that. And so it was less about Node and more about JavaScript, and injecting malicious code in JavaScript was still way too easy. We were using then a package called VM2 that was a sandbox that can run untrusted code, with whitelisted Node.js built-ins securely. So that was the claim of that VM2 package. And I'm showing you the sneak security vulnerability side for a reason, because if you scroll down a little, you see that, well, it still allows sandbox type, sandbox escape, arbitrary code execution, remote code execution, etc. And since May 2023, they stopped developing on it, still with those critical vulnerabilities available. So yeah, it's not what you want to have. So hey, let's roll on. Let's create our own runtime. Let's take that what we have in Deno already and make it suitable for applications. There are some performance trade-offs to that. So we're creating this new context over and over and over again. Puts on a couple of milliseconds extra time, but for the gain security, this was totally worth it. So yeah, we basically created our own runtime using Denon by providing our own global scope, making sure that nothing that should not escape the runtime can escape the runtime, and with the extra benefit that we can throw away everything after every execution. And now if you look at Lambda and what we did for ourselves in the runtime that runs on Lambda. Usually if a new Lambda invocation happens, it creates a sandbox with Firecracker. It downloads the code, your application, then it bootstraps it, which means it connects it to the Lambda APIs, and then it runs your code. What we do in the Dynatrace JavaScript runtime is we create a new VM context on V8. Then we load the code from the disk. Then we bootstrap the global symbols, everything that is Dynatrace related, and then we run the function. This is very similar. So I extra made it like that so that you see this is very, very similar. And that's true. So basically, we did the same process inside the runtime that the infrastructure does for us already. So when running Lambda, the first part happens, and then the second part happens. For added security, there's just a big difference. This here is pretty heavy. And the other thing down there is actually very lightweight. Just up there, it's a couple of 100 milliseconds. Down there, it's, I don't know, 50, 60 milliseconds, something like that. So moving to a custom runtime allowed us to recreate new VM context when VM already runs, when V8 already runs, the JavaScript engine from Node. And this is much, much more lightweight than booting up a micro VM with an operating system. And this little overhead had actually a massive effect. Every run is fresh and new. Every invocation starts anew and has no remnants from previous executions in memory of the scope. And this is actually a very good thing for something that wasn't so nice for us, which was Azure Functions. So, who runs applications on Azure Functions? Okay. Who likes running applications on Azure Functions? Okay. Yeah. Okay. So the thing is, we tried it out and it looked nice, but the moment you have a couple of extra things to do, things get very nasty very early. Remember that we wanted to go multi-cloud. This is one thing that we wanted to do. And please remember the image from earlier on. I told you it comes back. Just look at it for a second, and it will come back. So this is how a regular Azure function looks like. I guess it's version 4. I stopped bothering. I stopped at 3. And you have the same thing. So from squinting a little bit, tilting your head, it looks the same. You have some HTTP response, and you have a function that has a request in the context, like the event in context. It looks like Lambda, but it isn't. So there's lots of differences from Lambda and to Azure Functions, especially in those things that we were concerned about. First of all, CPU and memory, where we can limit CPU and memory on Lambda really, really good. In Azure, it's like, oh no, it's elastic. As much as you need, you get, up to a maximum limit, of course, but as much as you need as you get. If you run JavaScript, or if you run a browser, it takes all the memory that you can have. And also, if you run JavaScript code, it takes also at least one CPU to run that stuff. Invocation-wise, we have one instance per invocation, which was good for crashing, error handling, and whatsoever. Azure Functions are actually servers. They provide you with servers, and they take a couple of requests up to 200 that before they spin up a new instance. And you need to have a runtime that can handle multiple requests. Error handling, I told you already. If something on Azure on Lambda kills, well, then just respawn it. It doesn't affect anything else. If you have an error in Azure Functions, it kills the entire process. The entire process with every other request that's running in parallel. So, because it's a server. If your server crashes, all your requests crash. Which also means if you have noisy neighbors, well, they are noisy. And especially if you run them on the paid version of Azure Functions. You have a couple of apps deployed in one. I forgot what the granularity was, but you have lots of apps deployed in the paid version of Azure Functions. And one of those apps takes up all the CPU. It takes up all the CPU also of the other apps that you have deployed. So you have lots of noisiness. And again, I'm not saying that this is bad. It's just a way that doesn't align with what we wanted to do. We are an intermediate cloud provider, which means that, or an intermediate infrastructure provider, which means that we run untrusted code. If I can trust my code, then I could use Azure Functions just fine. But in that case, we don't know what we are running. We don't know what's happening. We can't debug it for the infrastructure, because every developer that works with us should not take care about the infrastructure. And this is why all the things that Azure Function provides for us, even though they have a very similar model, in terms of consumption-based pricing, auto-scaling, whatever, and just writing a little bit of JavaScript code. It was so fundamentally different for us that we weren't able to use Azure Functions nor anything of the other solutions that we had. And yeah, and it was expensive. So we were calculating around, let's say, I'm not saying so I'm not allowed to see the exact dollars. Let's call it goofies. So we were paying 20,000 goofies for a year on AWS Lambda. We were paying 40,000 goofies a month for Azure. So you can figure out yourself what a goofy is now in dollars or euros. And again, let's call back. Solutions are developed for a specific use case. We know that, and this might not be yours, and it was definitely not ours. So we were trying to fit our application model again into that box that wasn't ours. So the last decision that we made is the one thing that we wanted to avoid from the beginning. We rolled out. We created our own serverless platform, and we called it Kappa. Kappa because it's yeah, a couple of people already realize it. So Lambda is a Greek letter, Kappa is a Greek letter. They are very close to each other. And you know, everything in the Kubernetes ecosystem starts with a K. So that's cute, like Kappa. And that's what we did. So what we realized is a couple of facts. We realized that the function itself exposes no knowledge of the underlying infrastructure. The infrastructure has become a necessity, but not something any developer is concerned about. We respawn VMs with every invocation because of security reasons, which means that we have already some sort of serverless platform inside the serverless platform. And the application concept doesn't exist anymore. So deploying applications doesn't exist since we had ad hoc function. It's just JavaScript code that you execute and throw away in the end. All we needed was a place to run it that limits CPU and memory, and that's it. And that's actually what Kubernetes provides. So what we did is we were just removing the AWS Lambda part, and we created a series of worker pods. It's called around 80 worker pods that run the Dynatrace JavaScript runtime, oblivious of any application that is there. All they do is they are connected to a queue, to a RabbitMQ queue, and grabbing tasks where it says execute this function. The function lies in the function store. It loads the function from the disk, executes it, and puts the result back. Throws away everything, and then potentially works on a totally different app in the next call. All in Kubernetes and all pre-provisioned. All, again, limited. So if we look at what Lambda gives us for our case, what we have in Kappa is very, very similar. So first, we have scalable and hard limits per instance. We can do that. We can say you just get 256 megs of RAM and a quarter of a CPU. We have multiple instances that work on any code that they get. If it's ad hoc code or if it's code that runs on the disk, it doesn't matter. All they do are code execution machines. And they have access to the code and then they throw away anything. And this is also very similar on how Lambda handles it. Lambda has a couple of firecracker VMs running, and they refresh it with new operating system and runtimes again. It's similar to what we do, except that we don't install a runtime. It's already there. If something fails on AWS Lambda, the firecracker VM is being killed and respawned. And we have health probes in Kubernetes, which means that if this health probe doesn't react, we can kill the pod, restart it anew. No issues with noisy neighbors. And in scale, you know, we have already about 80 workers deployed, which is about the average workload that we expect, or no, the maximum workload that we expect. If we see that we have that we need more, we can scale nodes based on Kubernetes, and which takes a little bit more time than Lambda, but you know, which gives us we have some leeway on how we can see that. If the queue becomes too full, then you know, okay, please in the background spawn up a new node, and then we have more workers. So this is much, much closer to what we wanted. But the journey in there was to see how we failed, or how every challenge that we had led to a runtime that was capable of much, much more. Coming back to the image. I want to raise the question if anybody of you knows what this image should depict. Any idea? Do you know Super Mario World? It's actually the German strategy guide of Super Mario World. Oh, sorry, that was too fast. It's actually the German strategy guide of Super Mario World. This should be Mario, this should be Yoshi. The dolphin over there is also over here. That little birdie here is actually, if you manage to solve every level, also the special levels, those bullet wheels transform into birds. So this is, they knew what they were talking about, but this was very, very close game. And yet molds, and I think he didn't know how to. He didn't know how to put that mold not into the water, so he gave a little swim utensil. So yeah, the thing is, this is exemplary for, if you look at those two JavaScript functions from Azure Functions and AWS Lambda, they kind of look the same. You can see what they were thinking about when you mimic it. But nowhere in the world would you have thought that this was a 16-bit jumping around with the plumber and with Super Mario. So even though there's some similarity to it, it's not what you were looking for. What we have actually been looking for was something like this. There you go, animation. We wanted to have a fast 16-bit jump and run game. We wanted to have something that, if you look from a different perspective, provides you with the right scaling parameters, provides you with limited instances, is able to execute any code from anybody. So even though there are lots of serverless solutions out there, and they kind of all look the same if you look at the code that you write and deploy, the way they are executed are fundamentally different. And this is why we successfully failed to create our own serverless platform, because with every decision that we made, gearing on how can we run untrusted code, we finally made it, once we made to Azure, with a very little setup. We just needed a RabbitMQ and some Kubernetes pods with our runtime. The funny thing is that from the one thing that we didn't want to do, we didn't want to have anything self-written. We didn't want to fall into the not invented here fallacy. We ran into the everything invented here fallacy. So we have our own runtime. By the way, we still use Deno, but it's not recognized anymore. We changed so much from Deno and have written so much on our own that the only thing that we currently use are those VM bindings. We've written our own Kubernetes setup to distribute those workloads. We developed our own application model, our own function interface. But all those things are long-lasting. They last for years now. And you as a developer don't realize it. And those decisions were all important. So there wouldn't have been Kappa without our own Dynatrace JavaScript runtime. There wouldn't have been the Dynatrace JavaScript runtime without the need for ad hoc functions. The ad hoc functions couldn't have worked without the universal function interface, where we removed everything from the invocation details. The universal function interface wouldn't have happened if we wouldn't have abstracted serverless, because we wanted to go multi-cloud at one point. And yeah, no abstraction for serverless without the need for multi-cloud. The learnings that we had is, first of all, in the beginning, don't try to account for all possibilities. Start small. The decision to choose Lambda and just to run through it for a while was very, very good. But also don't overdo it. So once we knew that we could create our own function interface, we had lots of ideas on what to put in there. It was much, much more important what we didn't put in there. And you know, I'm very, very strict about it. Every time somebody comes to me and says, you know, we could have a second parameter in the function interface and do all that great stuff. I said, no, the function interface stays like that. It's supposed to stay like that because we also don't know in the future where our code will run. And this is the easiest interface that you can get. Yeah, and the developer-focused product, App Engine should put developers first, which also means abstracting away the infrastructure from that function interface was important so that people could focus on applications. Yeah, and not only ask yourself how you can read something, how you can create a serverless backend for apps, but also how you can move away from things. We knew that we weren't going to stay for Lambda until the end of the days. It was helpful for us, but since we are now running on Kubernetes with those workers, we are putting Kappa on AWS as well, not only Azure. and very painless. So it's actually not something that bothers us too much. And with that, thank you all for your attention. Thank you for joining my therapy session. I'm still here if you have any questions. Thank you very much. I'm sweating 2 minutes away, but anybody has any questions? Yeah.
How does the development cycle work? Do you have like an offline version of it to develop it on your machine, or?
Yeah. In 2 weeks, the same Dynatrace JavaScript runtime is being deployed on your local machine as well. Right now, we still work with the runtime simulator that is written in Node.js, mainly because all the APIs that we provided for the Dynatrace JavaScript runtime are the same for 3 years now, and we started out with the Node runtime. So we were still the Node runtime still exists if you install it locally and work on it. And locally, you don't have those security implications; they don't matter to you. But in the long run, it's a challenge to maintain 2 code bases if you want to fix bugs, etc. Yeah. Anything else? Yeah.
Did you have to write your own Helm charts or Kubernetes operator to do this?
So I have to admit, I don't know jack shit about Kubernetes, but yeah. So we have our own Helm charts. I can't tell you what's in there. Not our own Kubernetes operator. We have a self-written Kubernetes operator, but not for it. This is just, yeah. We have one endpoint for the RabbitMQ, and once this pod exists, it looks for the RabbitMQ endpoint, and that's all it needs to do. Yeah.
Why did you choose RabbitMQ, not something like job
Because we already had it in our systems. So that's also a very pragmatic decision. There's another component at Dynatrace which allows you to, so everything is sandboxed, and we make sure that we don't call any external URLs. We have an allow list. You need to allow certain HTTP endpoints to call them. And some people have the HTTP points they want to call within their own premises, especially with our customers. And they're able to install a small, also Rust-written component where they can connect to Dynatrace, and they get a fake HTTP URL from us, which means that we can call into the inner networks of companies from our serverless backend through this relay that people install locally. And this feature already uses RabbitMQ, and we had good experience with it, and that's why we just, oh, cool, this works, put it there, it works again. So that's the reason. Not more cloud native. You mean some existing SQS or stuff like that?
Yeah, like Nuts, for example.
Say again?
Like Nuts,
okay. Maybe also because of multi-cloud. So we can take what we have on Azure now and just distribute on AWS, and it just works. And I guess you can have a managed RabbitMQ on AWS as well, but I'm not entirely sure. Yeah. Yep.
Did you stop? No, go ahead. Okay. Did you stop at Azure functions, or did you explore other?
We looked at everything that Azure has to offer, which has everything that Azure has to offer in terms of auto-scaling and untrusted code. And there were a couple of things, I guess, was Azure batch processing, was it called, which was actually very close to what we wanted to have, but still failed in a couple of details. And going back to that particular slide, we could have managed it. We could have managed to work with Azure Batch or the Cloud Run equivalent of Azure Container Apps. We looked at that as well. We could have managed it. But in the end, everything that we got out of those by looking at our own runtime was that, it auto-scales. Kubernetes can do that on its own. So we made it much simpler by running our own. And much cheaper. Don't tell me.
I wanted to ask if this thing would have been able to run on Cloudflare workers, for example.
No. Cloudflare workers. We looked a lot at Cloudflare workers. We work with the people who write Cloudflare workers because we wanted to provide the same APIs. So there's the Winter community group that normalizes APIs across server-side JavaScript. We are not a member, but we are in close contact with them. And Cloudflare Workers is way too restricted for what we do. So we have tasks running for an hour if we do batch processing. Cloudflare Workers run only a couple of milliseconds because they are intercepting HTTP requests in the edge. So that's unfortunately not the right thing for us.
That's basically my question too.
Okay.
Because what you built, it looks a lot like what Cloudflare does, or the Azure cloud providers with V8 with their own Rust not run.
What we do and what Cloudflare does, same thing, same customer requirements, and we're in close contact with them, especially with James Nell, who I had the pleasure to meet as well. And maybe we just wanted to do it ourselves. But there's one particular constraint. Is Cloudflare is its own cloud provider. We wanted to be multi-cloud. And for reasons. So some of our customers are not able to run in other clouds. They need to have Azure, for example. We have customers whose requirement is to not run on AWS. So, and this is something that we need to account for. Ready? Cool. Thank you again for your attention. Thank you again for joining me. We are on time, I guess. Yeah. Perfect. Fantastic. So, and if you have some more questions that should not be on record, then I'm here for the next half hour. Very good. Thank you.